So our next session, which is our last session in the morning, will be the AI in security. And I'm going to introduce our next speaker, Rajarshi. Rajarshi is the head of AI for Avast, which is also a security company. And he got his PhD from Berkeley, then worked in Qualcomm research for many years. He has more than 175 patents, the most number of patents I've ever known anyone created. So let's hear from Rajesh.
Thank you, Junling, for that introduction, and good morning, everyone. So as you can tell, if you've seen it, my slide title says, security is AI's biggest challenge and AI is security's greatest opportunity. That's quite a handful. So let me begin by asking everyone a very simple question. How many of you in this audience have either read the Harry Potter books or seen the Harry Potter movies? Perfect. So at the beginning of book 6 in the Harry Potter series, there's a very fascinating exchange between the Minister of Magic, who pays a visit to the human or Muggle Prime Minister of England. Now, at this point in the series, the evil wizards or the Death Eaters have been causing havoc over England. I mean, they're breaking bridges, killing people, causing storms. And so the human Prime Minister is very scared and afraid and frustrated at what's going on in his country. And he asks the Minister of Magic a very important question. He says, "But you guys know magic. Surely you can solve anything." And to this, the Minister of Magic replies sadly, "You see, Prime Minister, the problem is the other side can do magic too." The other side can do magic too. That is why security is AI's biggest challenge today. It's the only domain of AI where the other side can do AI too. I mean, I love AI. I've been working in this field for many, many years, and I absolutely am thrilled by the advances that we have done in this area, how we have pushed the frontiers of AI in the last decade. So much so that the normal human being almost thinks of AI as magic. But it's this one domain of AI, it's security, where we have to deal with an adversary. We have to deal with a true adversary. I mean, if you think of all the domains of AI, like video and scene understanding and NLP, translation and audio, self-driving cars, in none of these domains is there a true adversary. And by true adversary, I mean someone who is as smart as we are and who has every economic incentive to use the best tools in the game, including AI. It's the only domain where the other side can do AI too. At the same time, AI is definitely the greatest opportunity for security today. The volume, the velocity, and the variety of attacks that are happening today is so fast that traditional algorithms in security just can't keep up. We need algorithms today that are adaptive, that quickly learn from what is going on in the network, and that can change itself. These are all definitions of an AI algorithm. And so indeed, we are seeing the security industry continuously adopt more and more and more AI techniques in their battle against the black hats. Good morning again. I'm Rajarshi Gupta. I am the head of AI at Avast. If you're familiar with AVG, we acquired AVG about 2 years ago, and the combined company is the world's largest consumer security network. So every single day, we protect 300 million PCs and 150 million mobile devices. So 450 million users requires quite a bit of scale, and there's a bunch of statistics there, but something like we process 300 million files and 200 billion URLs every day. So I noticed that in this conference over the 3 days, I have the only security talk. So in this talk, obviously there's not enough time to go over everything, I will focus on 3 very interesting problems in security: doing malware detection in the cloud, doing network detection for IoT devices, and how to deal with the current and ongoing threat of adversarial AI in the field of security. Now, I will in general talk about the advances that security has made in the field of AI and how AI is being uniquely used in the area of security. But of course, I will draw inspiration from our battles in the trenches every day and from the examples from our company Avast. So let's begin with malware detection in the cloud. This is a picture of the multi-layer anti-malware pipeline that Avast uses, and I will not go into the details of every one of these. The key point in this slide is addressed right up there in the heading that says that advanced threat detection and prevention has no silver bullet. If you are thinking that production quality, massive scale antivirus happens with a single thing where in comes a file and out goes an answer that's good or bad, that's not how it works. In reality, there's a conglomeration of several dozen different little engines, several dozen pieces of code that were literally developed over decades of experience. And these pieces of code all need to work together harmoniously in order to defend against many different types of malware. Indeed, in the last 10 years or so, us and many other companies in the security industry have adopted machine learning heavily. And today, if you can see, 5 of our 6 layers depends quite a bit on ML. But even there, it's not a single homogeneous machine learning model. It's a combination of many different models that work together in a sort of ensemble, but in reality, it just goes one after the other to try and detect the many different types of threats that is ongoing. So there are machine learning models, non-machine learning models, which all need to work together. As I said, the scale is very large, 200 billion URLs, 300 million files every month. Now, this is the AI Frontiers conference, so I will dig deeper into the ML piece of it. If you look at the pipeline of our machine learning model, it's very similar to any other classifier. There is collection, extraction, training, and execution. But what's interesting is if you dig deep into each one of these. First of all, there's nothing fancy about collection. The more data you have, the better it is. And in our particular case, these machine learning models for malware detection are built with about 400 terabytes of data. So 400 terabytes of data that includes good files and bad files. Straightforward. Second stage, extraction. What we have here are over 500 features that we extract from every single file. And these features are handcrafted features. They are done over decades of experience by security researchers who vouch for the fact that these are the important features that determine whether it is malware or benign. 500 plus handcrafted features from 400 terabytes of files. So now you want to build a model. As you might imagine, this takes a while. So what we ended up doing was to do a divide and conquer approach where we first run a clustering algorithm, an efficient clustering algorithm to divide the 400 terabytes of data into roughly 3,000 clusters. Now, you will know that clustering can only take you so far. So some of the clusters are very tight and very homogeneous, and the other clusters are kind of diffuse and heterogeneous. So when we take the next step, which is to build the actual classification model, we don't try to build one humongous model over the 400 terabytes of data. We go ahead and build 3,000 different local experts, each expert tuned to each one of these clusters. As you might expect, the classifiers for the homogeneous clusters are very short, very shallow, and very easy. The ones for the diffuse clusters are longer and more complex. And once again, as you might imagine, the reason you do it is that when you are trying to execute or a new file comes in, you first find the nearest cluster, and then you run the classifier. This whole algorithm is very parallelizable. It runs across a ton of different servers, and it's all fast and good. So that should be obvious to most people here. The more interesting thing, the much more interesting thing, is that we can do this entire pipeline from new feature selection all the way across training to deployment in less than 12 hours. Why is that important? Imagine you are trying to build a classifier for something normal, like you're trying to build a classifier to detect horses. So if you are trying to detect a classifier to detect horses, the underlying statistics, the underlying physical characteristics of horses hasn't changed in thousands of years. So there is really no need to redeploy or create a new model terribly often. Even in the case of self-driving cars, the underlying statistics changes in a matter of seasons. So there is a lot of time to do this thing. In the security industry, though, when a new malware thread or a new malware strain is exploding into the wild, the underlying characteristics of what a model looks like or what a malware looks like itself changes in a matter of one day. And that is why it's extremely important to have a pipeline which can react very, very quickly and get redeployed in 12 hours. Of course, we are pushing from the realms of clustering and classification to neural nets, just like everybody is. And I want to highlight one piece of work which my team published in ICLR earlier this year, where the goal was to augment our traditional handcrafted model with machine-generated features. And what we did was to build a large convolutional neural net using the raw bits of the binary files. So we took 20 million files, good files and malware files, and we challenged the deep neural net to understand the structure in these files purely from the bits. And to our very pleasant surprise, we realized that the model can actually do that. It is actually able to get to a point of accuracy that's nearly as good as handcrafted features. And around the same time, two other research groups in the world also did a similar exercise and validated because they saw the very similar sets of results. Now, so what do we get with this? We get one set of handcrafted features, which gives us good accuracy, and another set of raw binary features, which can be combined together to get a little bit better accuracy. So these features are somewhat orthogonal. Now, I'll be very honest. The handcrafted features are very cheap to compute. The raw binary features are horribly expensive to compute. But the most important point is that the binary features are terribly difficult to copy or to predict. Hackers spend millions of dollars to try and break our classification algorithms. And one of the best things they can do is identify exactly which features are we using. These raw features are very, very difficult to copy. And we love the fact that we are getting these new kinds of features, even if expensive, which are hard for the hackers. I will change gears a little bit and talk about doing malware detection on IoT devices from the network. Now, if you're like me and you have a LinkedIn feed and you read the news, you see lots and lots of stories about IoT security being a big threat. I'll give you my personal opinion that it is a big threat. It is a big threat because of a number of reasons. We have a bunch of devices, I mean like millions of devices, which are all connected into the world. We're connected into the internet. These devices are built by companies who have consumer experience and pricing at their heart. They don't think of security. They all have software which gets old very easily, but they're rarely or ever patched. And finally, the biggest problem I see is that you cannot put any security software on these devices. The best you can do is look at them from the network. So even with this plethora of problems, the security industry in general thinks that this is a solvable problem, and a whole bunch of companies, including ours, is trying hard to attack this problem. And the fundamental idea there, or the fundamental motivation there, is that each IoT device is quite limited in its applications. And the IoT devices have behavior which is structured and repetitive. Now, those two words, structured and repetitive, are words that machine learning people love, because structured and repetitive behavior is easy to model. And when we can model these behaviors, we can do anomaly detection too. So I'll use this as a very simple motivating example. This is the flow diagram of a little video camera before and after the Mirai infection. So at the beginning, you'll notice that the camera is going its own sweet way, it's talking to a few places, has a few flows, and then the poor guy gets affected by Mirai. Its behavior changes completely. It starts to send out thousands and thousands of flow requests to thousands of IP addresses. If you just took a glance at this diagram, you will immediately say that, hey, something drastic happened at that point of infection. And indeed, it is that simple. I mean, we built a very simple model which can detect Mirai, Satori, and all their brethren quite easily, because the behavior of a normal video camera is so different from the behavior of a Mirai botnet affected video camera. So let's talk about how the industry is going about solving this problem. Now, the main point here is to do traffic analysis. Sure, that's exactly what we do, but there are many nuances in there. So the key here, yes, traffic analysis means you evaluate the type of data sent, the amount of data sent, you calculate statistics, of course, mean variance stuff, but things like inter-arrival time, packet size distributions, distribution of IP addresses, and all the good stuff. And you do this not for a single device in isolation, but you do that for the whole class of devices to try and identify how the swarm is behaving. So yes, the key point here is to do traffic analysis for the entire swarm. But the cool thing is that the traffic analysis does not happen in isolation. The traffic analysis happens together with a lot of analysis of the infrastructure. You look at the traffic and you evaluate what kind of a network is the traffic coming from. You look at what kind of device it's coming from. And I'll give you a real interesting clue. For IoT devices, identifying or reliably and accurately identifying the device type is so important, because that one feature is like written in gold. That's one feature gives a ton of information about the capabilities of the device. In many cases, we can even tell the vulnerabilities of the device. And so we can not only predict what the good traffic should look like, in some limited cases, we even know what the bad traffic could look like. And it's this combination of infrastructure analysis and traffic analysis that together makes up the IoT device machine learning based protection. So let's look at the actual algorithms. I will broadly say that the industry is trying to tackle this problem with a two-pronged approach. The first approach is the traditional approach of building attack-specific models. So basically, you have your research and you identify that the IoT devices, the types of attacks are like denial of service, spread of malware, data leak, and then you go and build specific models, specific machine learning models to detect these attacks, and you put them together into an ensemble classifier. So this is the normal and the first approach that everybody is doing, and it's to be seen who does it better. But the second more interesting approach that I love is to build a deep neural net that is able to detect all of these attacks plus the unknown ones. And the way to do it is, think back to what I was saying like 7 minutes ago about building a deep neural net using the raw binary files of the malware. And here, replace the raw binary files with flows. So the way we do this is to feed in a deep neural net with flows that are coming from millions and millions of households. And we challenge the neural net to understand the structure in these flows, because there is structure. There is structure that a number of flows make up a device. A larger number of those flows make up a house, or in many, like thousands of flows across many houses, make up Netflix. So it's up to, so we challenge the neural net to understand these structures and understand these types of services that are happening on the internet, to be able, at the end, identify which of these are good and which of these are bad. And we want to do this because we want to autonomously identify the new attacks that we don't yet know about, the new attacks that are unknown to us at this point. As you can tell from my description, this is not a done deal. It's to be seen whether we can do it. I can keep you posted how we do. The third thing I want to talk about is adversarial AI. I mean, a lot of us have spoken about it, a lot of us heard about it, and it's a very genuine concern as to what is the security industry doing about that problem. In most of my such talks, I actually play this video, but I'm sure everybody has seen this video of President Obama using AI to have President Obama's face generate fake words. So I'm not going to play that. The point here that I just want to highlight is the fact that adversarial AI algorithms today are smart enough that they can quite easily fool humans with this kind of fake news. So the natural question to ask following up is, how do AI algorithms do against it? And this is another example which most of you should have already seen also. This is from my colleagues at Berkeley last year, where the adversarial AI algorithm was trying to fool a deep learning algorithm, obviously from the self-driving car domain. And the challenge was for the adversarial AI algorithm into convincing the object detector into thinking that the picture says speed limit 45. To the collective horror of everyone, and for some specific set of people like me who regularly drives a self-driving Tesla, to the collective horror of all us, they succeeded. Every one of these 25 pictures were classified as saying speed limit 45. So the key point here is that adversarial AI algorithms also find it easy to fool deep learning algorithms. So that's the state of the art. So what are we in the security industry doing about it? So to talk about that, I will introduce a term that we call deep attacks. And I will define this term as malicious content that is automatically generated by AI algorithms. So let me repeat. Deep attacks are malicious content that is automatically generated by AI algorithms. The examples that we just used are from the domain of video and images, and I've seen some audio examples too that are really, really good. But I will call these as upcoming attacks. Yes, the researchers have shown us that these are very real and they can be done, but thankfully, we have not yet seen any such attack at scale in the wild. On the other hand, we security people have to constantly deal with deep attacks that generate fake URLs and fake web pages. Deep attacks that generate fake binary files to fool our classifiers, and deep attacks that generate tons and tons of network flows to cause problems around the world. These are existing examples of deep attacks that we have to try and defend against. So I drew up, with limited amount of time, I drew up one simple animation cartoon to try and explain what are the kinds of techniques that we use to defend against these kinds of deep attacks. So let's talk about how the attack takes place typically. So there is an attacker on the side wearing a hoodie, and there's a very nice top-hatted classifier on the left. So typically, the attacker will try an example. And the classifier, being a classifier, says good or bad. And this one bit of information allows the attacker to learn a little bit about the classifier. You do this loop about a few million times, and the attacker learns enough about the classifier to be able to generate those fake examples at will. So this is how it works. So how do you defend against it? And I'm going to talk about 3 types of defense. It's probably not a comprehensive thing, but 3 common types of way to defend against it. The first defense is don't let that happen. I mean, why would you let someone try examples on you a million times? And we don't. We have very serious guard dogs. We have very serious watchdogs that are sitting on top of our cloud-based machine learning classifier to make sure that no one is able to attack the system over and over again. We track the number of queries and limit the number of attempts that can happen against our system. That is actually one of the reasons why cloud-based systems still dominates the world of anti-malware. Because when you have device-based systems, it can be taken to a garage and someone can test against it for eternity. But on the cloud, there are guard dogs to make sure that that cannot be done. The second defense is the algorithmic defense. So we, of course, build our own version of the attacker. And just like the attacker learns from the classifier and gets better, well, this time we let the classifier learn from the attacker, and they simultaneously get better. And this is, of course, the technique of using GANs to improve your classifier. The third defense is what I call offense is the best defense. We are actively building classifiers. We are actively building techniques to actually identify these kinds of attackers. We build targeted models to identify the handiwork of such deep attackers. We not only try to find out who is generating what content is being generated, we actually go for the source, and that's quite easy. And oftentimes it's easier to identify who is generating it than what is being generated. So the provenance of the files that are coming out, the metadata associated with the files are evaluated to great length to identify these kinds of algorithmic attacks. So those are the 3 major techniques that I am familiar with that are being used to defend against these deep attacks. These deep attacks which are part and parcel of our life and which makes us lose sleep at night. So I'm coming to the end of my talk, and as you might expect, from the beginning of my talk, I'm going to end this with one simple and direct message. If you are an AI researcher and you are really proud of your skills as an AI person, I'm challenging you to come and pit your skills against a true adversary. I want you to come and innovate in AI for security. Thank you.
Thank you, Rajesh. We have time for a couple questions. If in the audience, anyone want questions, put up your hand. Our volunteer will bring the microphone to you.
So one very basic question. When you mention malware in cloud, is that a piece of software that damaged the cloud as a general, or would that be effective if somebody downloaded and then it would damage like a personal computer?
So that's a very good question. It's the latter. So typically what happens is that a new piece of software or a new URL is accessed by one of our millions and millions of customers. And when it affects it, we in the cloud get to see it. We either get to see it because we get some metadata or get some features from that file, or in the worst case scenario, if this file has been seen for the first time ever, we actually put it into a quarantine on the local device and upload the entire file to the cloud to be able to analyze it and then help everybody else in our customer base. So the source of the information is always the endpoints.
All right. One last question.
Great talk, Rajarshi. Just one question for you. So as you think about this, dual-edged sword of AI fighting AI and AI creating new attacks. Where do you see this going? Do we ever end up in a situation, because right now there's a big discussion about interpretability of AI models. So do you ever end up in a situation where you have AI fighting AI and humans can't interpret what's happening, and what happens then?
Yes, I think that's a great question. In fact, one of the slides from this talk that I had to leave out here are what are the biggest challenges of building AI models, and that is like the #2 challenge, that security models need to be very interpretable. And that ties our hands somewhat, because as you know, a lot of the deep learning models find it very hard to be interpretable. And today, it's a common discussion saying, the AI team is building a model and says, look at the results. And the threat team is saying, but I can't use the results. I can't really use it until you tell me why you are doing it. So it's a very natural problem, and I don't know what the answer is the short answer. It is going that way, and we definitely have many models today which are doing very good statistics and then don't know the interpretation. So often what we end up doing is we take the output of the main model and we try to build further models to do automatic labeling and automatic classification. That's one of the ongoing projects in my team, is to take the output of the model, which is very, very accurate, and then run it through another model which actually gives you the labels of what it is trying to do or what kind of a malware it is. And this is important for our threat team to give an answer.
Great. Let's thank Rajesh. Thank you. So that ends our morning session. Lunch is from 12 to 1 p.m. Let's get back here at 1 p.m. and see you soon.